Okay, this will be the review for EE310 for the final. So we'll be going over all the topics past Laplace analysis. And so we'll just focus real quick on Laplace circuits, and then we'll do for your series for your transform and any other additional material that needs to be covered. Okay, so let's look at our specific types of systems we have. So we're given a circuit here. And this circuit has a resistor and an inductor. And so within the circuit, this voltage source, it's in the time domain right now. So we have V of t, then we have R, then we have L. And the current that's going through is given in I of t. The big thing here is to realize when you are going to do your circuit analysis, you can convert this into the frequency domain and then do Laplace analysis on it and convert it back into the time domain. And so if we're looking at this equation right here, and we're trying to determine what we should do. Well, first, if we make our specific loop around with our current, so let me write the equation we would do if we were doing the current through the circuit. If I'm the current right here and I'm going up a voltage rise, that's going to be a negative voltage. So I'm going to have negative VT as I'm going through because it goes up a voltage rise, and then plus, and then it's going to be R times I of t because the current's going to travel through a resistor and cause a voltage drop. And then the other voltage drop, remember Eli the Iceman, E was the old notation for voltage, and the derivative is always the last one. So Eli, the old symbol for voltage, L di dt equals 0. And now what we can do is we know from our Laplace analysis, basically what we can rewrite this expression using the Laplace domain. And so if I take the Laplace, I can move the voltage real quick over to the other side, then take the Laplace of both sides. And so it would be R I of t plus L di dt equals V of t. Okay. Now I'm going to take the Laplace of both sides. And when we do that, Laplace of this side.
Quick question. Did I miss anything?
No, we're just going over circuit analysis right now and using.
Oh, so this is just the first page?
Yeah. Mm-hmm.
All right, thanks.
So we just wrote the equation when we're doing the current going through each of the elements, wrote all the voltage drops, then took the Laplace of both sides. Now that we took the Laplace of both sides, what we need to do is, okay, what's happening here is we see we have our one term sort of like x, and then we have the derivative, of x, but right here it's representing current. And so what we know when we do the Laplace transform, if we look at the table in particular, the Laplace transform has of a term like this, the derivative. What's going to happen to it is it's going to be in the format, if you guys remember, L, and then it's going to have S I of S. And then what happens is you lower one power of S as you go along. So you deduct one, so it would be S1. So this would actually be S0. S to the power of 0 is just 1. And then it becomes your initial condition also when you look at the Laplace table as it approaches from the left-hand side at time 0. And then for this R I of t, what that's going to become is just R I of S. The R is a constant, but your IT, when you convert that to the Laplace domain, you just go from the time to the frequency. And so we just use the capital I and then S. Right here, the L, remember that's a constant, so that's why it's outside here. And then derivative, when you take the Laplace of the derivative, you get S and then the frequency domain representation of your variable, and then you minus, and then you lower the power of S, and then you do the first initial condition, and then you say equal to, And then if we take the Laplace of VT, that just becomes capital V of S. Now in the frequency domain. And now you formed your equation for the circuit in the frequency or S domain. And so you can write it out so you get all your terms. So it would look like Ri of S plus, and then L-Si of S minus Li of 0 equals V of S. And that would be your equation you have for that circuit. And then if you had any initial conditions, that's where they would go into. And then you can do all your operations to either find the current or in order to solve for one of the variables, and you could transform it back into the time domain using the inverse Laplace transform. And then what we're going to look at in particular is what if we have a capacitor now in the circuit? So our circuit now became a current source instead of a voltage source, so I of t. And here we're going to have R for our resistance, and then we're going to have C for capacitance. And so what is going to happen here? And so what we're going to notice is when we are going to make our equation in particular, you will see that our current, basically, some of it is going to go for the resistor, and the other part of the current is going to go through our capacitor. And so an important thing to take away is when we're looking at our current in particular, the current that is entering this point right here, it's going to be split. So this current's coming in from the source to that point, and then some of the currents can go down for the resistor here, and some of the other currents can go for the capacitor here. So when I make my equation at this node, what's coming in is equal to what's coming out. And so what's coming in is I of t. That's what's coming into the node right here. What's going out is some of the current's going to go for the resistor and some is going to go for the capacitor. And so to represent the current that is basically going through the resistor, it would be, because the current coming in is equal current coming out, and the current going out is these two arrows pointing down here. Some of that voltage is going to be on the resistor, so that'd be your V of T over R. And then the other voltage is going to be on the capacitor here. And so, some of the current is going to go for the capacitor, and that would be given by C dV dt. That comes from Eli, the Iceman, the ice part, C, and then the old version for E was V, the old notation. And so now we got our equation for current coming into that node is equal to the current going out of the node, which is these two right here. And since we know that, we can now use our Laplace analysis to both sides. So Laplace of both sides, when you take the Laplace of both sides, when you take the Laplace of both sides here, what you're going to notice is you're going to get a capital I of S is equal to, and then here, this is a constant, right? 1 over R. And so it's going to be just 1 over R. And then when you take the Laplace of V of t, it just becomes capital V of S, and then plus C is just a constant here. But this is a Laplace of a derivative. And remember, when we have a derivative, just like above, when we had the derivative here, and we had to do the Laplace of it, it's going to become S V of S minus, and then you drop 1 in the S for the exponent, so it'd just be S of 0 here, so it'd be 1. And then you do the initial condition, so V of 0, and then approaching from the left-hand side. And then, now since we got our I of S here, what you can do with this is you can just distribute the C. So become I of S is equal to 1 over R, capital V of S, plus, and then here it'd be S C V of S minus C V evaluated at time 0. And so then that's how you could solve for it. and then you can convert it back into the time domain if needed. And then what we will notice is basically when we were dealing with an inductor here, right? So this is our inductor. Let me get my highlighter real quick. We saw when we took basically the Laplace domain analysis of this LdIdt for when we're looking at the current that was going through the inductor and what the voltage drop would be, we got in particular this equation right here. This was the part that was from the inductor. And then when we're looking at the capacitor here, we noticed that contributed this part to this equation here. And so what we're going to say is when we have an inductor in the time domain, so let me make a difference here, time domain versus frequency domain. Okay. When we have an inductor here in the time domain, basically what you're going to notice is that the voltage of an inductor is given by V equals L times di dt. And so in the frequency domain, how are we going to represent that? And so when we're looking at the frequency domain, we're going to see that the voltage actually on the inductor is given by these two parts here. And so it looks like there's an initial value in particular in correspondence with that inductor's value current that is running through it. And so we represent an inductor in the frequency domain with an inductor and then a voltage source that accounts for that initial condition here. And so in the frequency domain, what this is going to be, so we're going to have S of L, and then we're going to have the initial voltage on it, Li of 0 minus. And so that's what we have here because we have the current that is going to be running through this inductor, which is given by I of S. And so this just takes into account the initial condition. And this is your inductor in the frequency domain. You use S of L to represent an inductor, but it will have the current in the frequency domain running through it. And then this initial condition, why it is in this position, deals with relatively, it's minus sign up here. And then our next one is our capacitor in the time domain versus the frequency domain. And so our capacitor, it's given by, in the time domain, we use the equation I equals C dV dt. Remember Eli the Iceman? That's where this one's coming from, the ice. And then what's happening right here is we see in the frequency domain, we have the exact same issue where we're having right now initial condition in addition to because we made an equation for current and we noticed that it wasn't only just a capacitor, but it's a capacitor with a voltage at the initial condition as well. So here we have our capacitance, which we give as 1 over S is C. And then we have our voltage source here, which is given by V0. So the voltage at time 0 over and then S. And you can derive that from this equation up here in order to get what it represents. But that's just how these come into being, that they have different representations in the time domain and frequency domain. So if you were to convert this circuit up here into the frequency domain, what it is going to look like is basically you would notice that your source, you'd still have V of S instead of V of T. Your resistor stays exactly the same, but your inductor here, knowing what we know here, it's going to have still a coil for your inductor, but it'll have the initial condition as well. So minus and positive. And so this would be your resistance still, your inductor S of L, and then you would have L and then I, the initial condition taken into account. And then here, if you were to redraw this circuit in the frequency domain, no longer in the time domain, so it's probably good I say time domain here, and then this would be the S domain. And this would be the time domain. And then down here, let me just draw real quick where you're going to see this one in the frequency domain. So remember, you have your capital I VES, and then your resistor stays the same, frequency or time domain, but the capacitor we'll see it's given by right here, the conversion. So we would have our capacitance and then the initial condition taken into account. So this would be our R, 1 over S to C, and then this would be the voltage at time 0 all over S. And so here's where we got our equivalent circuits for that first part in his lecture. Now that we have discovered how those were taken into account, we're going to do an example where we're going to go over basically one of these responses in order to get familiar with how we should approach some of the problems. So we're going to see the response of a low pass filter to a pulse input if the system was at rest at time 0. And so right here, we're going to be given this type of circuit configuration. And there's going to be a pulse at time 0. So 0 to 1, and it's going to be 1 volt. So this is 1 second, 0 seconds, 1 second. And then we're going to have a 0.5 mega ohm resistor, and then we're going to have a 1 microfarad capacitor. And then this is the output voltage here, V out T. And then here's the negative terminal. Okay, so what it wants is it says find the response V out of T. So find V out of T's response. And so what we should first do when we see this particular circuit, we can tell it's given in the time domain. That should be running through your mind. Okay, he gave me a circuit in the time domain, and if we're in this class, it's signals and systems, so we should be dealing with the frequency domain, right? So what I would do when I first see this is I would think, okay, now that I'm given it in the time domain analysis, how should I convert this to the frequency domain? And so what should be going through your mind initially is, okay, here's my voltage source, here's my resistor, that stays the same, but here's my capacitor. And remember, my capacitor is given by an equivalent capacitor, which is 1 over S to C, and then there's an initial condition. But it said in the top, it said the system was at rest at time 0. And so if you were to draw in particular what it would look like for your initial condition here, and if you had your V at time 0 over S, and then you drew the rest of your circuit, since the system is at rest, you can just ignore what you have here for your initial condition because the system was at rest. So there was no initial value of voltage on that capacitor. So literally you can just ignore this and create a short right there. And so now that we know there was no initial condition, this just evaluated to 0, so we could get rid of it. We know what our equivalent circuit's going to be. So it's just going to be the voltage source here. And okay, this was in the time domain, right? And so if I were to write a quick equation for the voltage source, so the V in of T, it's going to be U of T, right? It starts at time 0, and then it comes down at time 1. So minus U of T minus 1. And then if we were to write that in the S domain, V in of S is going to be equal to 1 over S. And then here we have a shift. Remember, and if we have our table with us, in particular for the Laplace analysis, what we should see is when we take a time shift, let me pull it up here so I can show you guys, it's just going to cause an e to the negative, let me, when you have your shift in the time domain, let's see if that can enter. Right here on the 2a, it's multiplied in the frequency domain, it's e to negative ts over s. So what we're going to notice is that it's going to become minus e to the negative, t is 1 in the sense, so it would just be 1 times s. So here would be 1 times s over, and then s. So you can simplify that. So it would just look like 1 over s minus e to the negative s over s instead. So it's better instead of having that 1 up there. Okay, so now you got your voltage at the source here, your V in of s. You got your resistor here, which is 0.5 mega ohms. And you got your capacitor right here. And you're trying to find the output response here. And so let's make an equation. And so to make an equation, basically, what we're going to see is if we do a current that's running through the circuit, so if we draw a current, which is I of S now, because we're working in the frequency domain, we're going to have R times I of S, and then plus, and then the current's going to run through here. So it would be 1 over SC times I of S. And then that is going to be equal to the voltage on the source. So the voltage on the source is given by 1 over S minus e to negative s over s. And so now we got the voltage on the source. We got everything, and we're trying to find V out of S. And so what we're going to do here, basically, let me see, is how are we going to find that voltage in particular on the capacitor? Okay, so we're given that okay, once we solve for I of S, do you agree with me that the voltage on the capacitor is going to equal the current times the impedance? And here's 1 over SC. So the current that's running through this will give me the voltage, right? And we're finding the current right now. And so the current I of S, if we, I of S, it's multiplied by R plus 1 over SC is equal to 1 over S minus e to negative s over s, and divide both sides of the equation by R plus 1 over SC. So I of S would just be equal to 1 over S minus e to negative s over s. And that's all over R plus 1 over SC. And so now I got it written in this format. And what we're going to see is that this numerator has a common term, which is just S. And so you can write it like 1 minus e to negative s, then all over, and then it's going to be s multiplied by r plus 1 over sc. That's the equivalent. So now we got the equivalent format. And now what we can do is basically looking at this equation in particular, if I multiply that s through, I'm going to get 1 minus e to negative s all over, and then this would be s of r plus 1 over c. And so my I of s is equal to all this. And so what I can do now is if I want to get my denominator in a way, I can specifically solve this. I know my values for R and I know my value for capacitance. I can plug those in to my equation here. So 1 minus e to negative s all over, and then this is 0.5 mega ohms. So 0.5 mega ohms times s plus 1 over the capacitor is 1 microfarad. Okay, so when I plug these in, and I have my calculator over here, what I'm going to get as a result is 1 divided by 1 microfarad. That gives me 1 mega ohm. So let me pens. Okay. So I guess. So we got 1 minus e to negative s. And then let me bring out this 0.5 mega ohms. And so it'd just be S. And then here, I'm gonna have plus, and then I took out this. This was when I looked at my calculator, this value was 1 mega ohm. So 1 mega ohm divided by 0.5 e-6, if I were to get that out, sorry, mega ohm divided by, and then 0.5 mega ohms, I got 2 basically. So you're gonna have S plus 2 down here. Okay, so now we got it written like this for I of S. And so now we have it in this format here. What we can do in particular is we can split this up into 2. And so I can write my I of S. It's going to be equal to 1 over 0.5 mega ohms, so times 10 to the 6, then S plus 2, minus e to the negative s all over, and then 0.5 mega ohms times s plus 2. Okay, so now what we can do is we can do 1 divided by 0.5 mega ohms. You should get 2 micro all over s plus 2. And then here you would get 1 divided by 0.5 mega ohms, so that'd be 2 micro e to the negative s all over, and then s plus 2. And so that's your I of s value here. And so now you know your I of s, that current specifically, that is running through there. And then what you need to do now is, remember, I told you guys the voltage output here is going to equal the current times the actual impedance of this device. But we found, because in the S domain, what you can do is, because now this is converted all to impedances, your voltage is just going to equal the current times and then the impedance. And so our V out of S is going to equal 1 over SC times I of S. And so, let me move my paper up real quick. Because we're working on the frequency domain, we can do this. And so that's going to be, and so if we have here what we were given, 1 over SC, then multiplied by 2 times 10 to the negative 6 all over, and then S plus 2 minus 2 times 10 to the negative 6, and then E to the negative S all over, and then S plus 2. And then you're going to see here, I'm just going to give you the steps on how to solve it in particular, because the rest of this, your capacitance is just going to be a constant, so you know. So that would just be divided by. But what you're going to notice is it's going to become S and then times S plus 2 in the denominator. So you're going to use partial fraction decomposition. And then once you use partial fraction decomposition, then you'll be able to write it individually. So you should get this in the end. After, what I would do is distribute, use partial fraction decomposition. And then after you use partial fraction decomposition, your result should be A over S plus B over S plus 2 plus C over S, and then plus D over S plus 2. And then you'll convert those back into the time domain. So convert into time domain. And that's where you'll use your Laplace table. But that's how you would get the specific voltage out. So what we did here is, from our circuit up here, I'm just going to start from the very beginning, give you a recap. This was in the time domain here, this circuit, and then we converted it to the frequency domain down here below. So we knew that a capacitor is converted into a capacitor with an initial condition, but the system was at rest at t0, so there was no initial voltage stored on that capacitor. Then we noticed the voltage here is given by a pulse, which is ut minus 1. And so we converted that into the frequency domain using the Laplace table. We were able to find both of these. And then resistor stays the same. So once we drew the equivalent frequency domain circuit, we solved for the current going for the circuit. And since we're now in the frequency domain, the voltage output here is just going to be the current multiplied by the equivalent impedance. And so the impedance is 1 over S to C, and then times that what we get for the current. So we found what the current was here after doing a lot of mathematical manipulation. So our output voltage is going to be the impedance times the current, and then that will solve basically what you'll do is you'll distribute this to both terms, and then you're going to notice you'll get a number on top over S times S plus 2, and you'll use partial fraction decomposition and convert to the time domain. And so that's how you could solve for V out of T. And now that we covered that, there we'll be going over op amps. And so how do operational amplifiers work? So let's take some notes on these. So operational amplifiers it's basically, it looks something like this. It's like a triangle shape, and then it has 2 ports to it, a positive and a negative terminal. And then it has an output here, V out, 2 inputs, 1 to the positive, 1 to the negative terminal. And then you have a supply voltage. And so you have a negative VCC and you have a positive VCC. And so basically what you're going to notice is there's barely any current coming into these ports. So if there's almost no current coming into here, that must mean that the input impedance is really high. So it has a high input impedance. And so that would mean like our impedance is like almost infinity at the input. But the nice thing about an op amp is the output impedance is really low. And so if you're trying to amplify like a really small signal, the op amp is really good for that because it will amplify your signal and get rid of any noise that can interfere with your signal. And so it has really low output impedance. So low output impedance. And the reason it has low output impedance, it's so that the signal can get delivered to the output. So whatever is going to pick up the signal and actually read or analyze it. And then the gain is high because an op amp, it's an amplifier. That's in the name. So the gain's going to be high. That's what the name literally says. It's an amplifier. So it's about infinity for an open loop configuration. And our output voltage is going to equal the gain multiplied by, and then what I always like to say is it's the positive voltage here, V of P, minus the negative voltage. So the voltage at the inverting terminal. So it's going to be the gain multiplied by the difference between the positive and negative terminal. I hate it when teachers say V1 here and V2. It's so much easier to know VP is a voltage at the positive terminal and V of N is a voltage at the negative terminal, because you can just do the gain multiplied by VP minus VN. Is it's always the VP, which is the higher potential, minus the lower potential, the difference multiplied by the gain, because that's what an op amp does. It amplifies the difference between these 2 terminals. And then your output voltage will be bounded. So output voltage is bounded. And this class is different from 211 because in 211, we said it's only within 1 volt of the supply. But for this class, he says it's right at what the supply is. So what does that mean? Is basically our supply here. If we have negative 15 volts and we have 15 volts up here, the most this output voltage can be is our output voltage is then limited within the range of negative 15 to 15 volts. Okay, so that's what an op amp is. And so we're going to look at one of the op amp configurations here. So I'm going to draw it over here and we're going to find the transfer function. So find the transfer function of the op amp. So here we are given an operational amplifier, which has a negative and a positive terminal. And we notice that there is an impedance here and an impedance here. It can either be an inductor, resistor, or capacitor that's in this one or this box here. We don't know particularly what it is, but we're just going to try and find the transfer function. And so here is our voltage input and then our voltage output. And we're going to have to determine the transfer function. So right here, this is always called the feedback because it's hooked back to the negative terminal of the op amp. So this is the feedback impedance, where this other one here, in our other class, we call it basically the one in the other resistors, the Z are always like the R of S, but this is with impedance, we'll just call it Z of S. This one doesn't have like an actual really name, just the S is always the one that's hooked, basically the other resistor. That's what I like to say, or the other impedance. The feedback one, it's always Z of F, but this one, they don't really know the subscript as well. It's usually just the subscript is S, but it doesn't matter. But our transfer function, the important thing of the transfer function is when I'm writing it here, it's going to be the output over the input. And that's when all initial conditions are 0 for your transfer function. That's an important thing to remember about your transfer functions is all initial conditions are assumed to be 0. And so here we have the output over the input, and our output right here would be V out of S all over V in of S. And so what we're going to notice is how can we get an equation for the output voltage over the input voltage? And so what we're going to do is we're going to use basically our current technique. So the current coming in to this terminal right here, there's going to be some current that's coming back from the output voltage. There's going to be some coming from the input. And then the one here that is going to be going into the device, because we're looking at this node right here, we're going to label this one I1, this one I2, and this one I3. So we have one current coming from the output back into the inverting terminal because that's the feedback loop. We have one that's coming from the input voltage, so that's I2 here. We have one at the op amp terminal. And so if I write my equation, what is going in and what's going out? So the two currents coming in is I1 and I2. The current that's going out of the node is this I3 here. And one important characteristic is, remember, this op amp has a lot of high input impedance right before both of these terminals. So this I3 goes towards 0 because there's so much impedance. It's literally like an open circuit almost there. So there's no current flowing through. And so now we're just given I1 equals negative I2. And so that basically tells us that our I1, which if we make an equation here, that node I'm going to label V of N because it's at the negative terminal, right? So if we make an equation, V of N, and then minus V out all over what's in between for the impedance, it's Z of F here, is equal to, and then it'd be the minus of, and then here, I2 is given by V of N minus V in all over Z of S. And so what we're going to see, oh wait, oops, did I draw the correction that now V in minus V1, V out? Oh, I think it should be fine though still, is I just drew it. So real quick, I just noticed I made a small mistake right here. When I have the arrow, I always do where it starts out from. So it actually be V out minus, and then is this where it starts from and where it goes to, minus Vn all over Z of F is going to be equal to negative And then this one, I2, the arrow starts from this side, V in, and it goes towards V n. So it would be V in minus V of n all over what's in between, which is Z of S. Okay, now that we got that, what can we do? And so V of n, remember, what we're going to see here, the voltage difference between these two terminals is minimal because it amplifies that almost by infinity. So the voltage at both terminals are roughly the same. And that's a pretty important concept to take away, is that V of P, I'm going to write that right here. Recall, V of P is almost equivalent to V of N in an operational amplifier. And so what we're going to see is V of P is set at 0 volts, right? And so since it's at 0 volts, that means this in this term will go towards 0 and 0. So you're just going to get V out over Z of F is going to equal minus voltage in over Z of S. And so now if we write this as the output voltage over the input voltage, we're going to get the output voltage over the input voltage is equal to negative Z of F over Z of S. And now knowing that, we have derived specifically the transfer function written in terms of the impedance. So it's negative Z of F over Z of S. And so that's how you would go about deriving the transfer function if you were given an op amp. And so what we did here is we just did nodal analysis at one of the nodes. We saw all the currents coming in, and then we wrote our current equation here. And then we knew that the current at the terminal, the op amps, it's about 0 because it has infinite impedance at the input terminals. So that means it has like a lot of high resistance at those. So barely any current will flow through those input terminals. So we said it goes towards 0. And then we said that the voltage at both the terminals are roughly about the same. So that's why we could cross out V of n on both of these. And so we could write now the output voltage over the input voltage. And so that gave us this equation here, which is the exact same thing as V out over Vn. So we could substitute in negative ZF all over Z of S. And so the basic op amps that you need to be familiar with when we're dealing with these type of operational amplifiers, there's 3 main types. I guess 4 actually that I feel that are necessary to know. He has only 3 here, but the inverting one is pretty popular. That's the one we just did, where we have a negative and a positive. And then since it's inverting, the voltage source is hooked to the inverting terminal. If it was non-inverting, the voltage source would be hooked to the positive terminal. So this one would be given just like I had here. It's Z and then S, and then hooked right up here. And then we have our Z of F, our feedback impedance. And then our output voltage over here, V out. And then we have this one hooked to ground. And so what we're going to notice is the output is going to be equal to, and then since it's inverting, it has a minus sign here. And then it's the input voltage multiplied by, and then Z of F over Z S. And then that's your inverting equation to get the output voltage. So your next one is going to be an integrator. So the integrator op amp, how does it integrate basically? And so what you're going to notice is your integrator op amp, it's going to be given by the input voltage. So it's going to have a resistor here, and then it's going to have a capacitor. So here's our resistor, here's our capacitor, and here's our operational amplifier. Have our negative terminal, and here's our positive, and here's our output voltage given on this side. Okay, for our integrator, basically, we need to find the transfer function. And so our transfer function, remember, is H of S is going to be equal to the output voltage over the input voltage. And that is going to be equal to, and then it's negative Z of F over Z of S, which was what we just found here, right? For the inverting terminal, the inverting op amp, same thing, but here now we have a capacitor and here we have a resistor. So I'm going to input their specific impedances in here. So it's -1 over SC all over, and then the resistance R. And so this is equal to -1 over SRC, which is right here. Resistance and capacitance is constant, right? This all here is constant. It's just the S term that's going to vary. So I can write that all as A all over S. And if you remember, going back here, let me look, is there the integral, which I want? Yes. Okay, let's see if this pops up pretty well. If you look at the integral, basically here, this is how you would prove it, it is right here. This integral one, I know it might be a little blurry, but it's 1 over S, X of S. And so it's for the time integral property. And so let me see. Yeah, no, sorry. That's not going to work. But basically the 1 over S block is the integral block. And so that's what you would use in order to notice that this is an integrator. And so now that we got the integrator one defined, let's do the summer. And so the summer, it basically shows you that when we have an op amp here, it's going to have our resistance. And then we're going to have 3 other voltages, or it can be more than, it's literally just more than one voltage source. But I like seeing it as V1, and then we could have V2, and then V3. And actually, I don't like his definition of just summer. I find it better to call it inverting summer, because it's going to invert all those input voltages. And so you're going to see why. But here we'd have one resistor, R1. There's our next resistor here, and our next one here. I'll just coordinate the names with the voltage numbers. So this would be R1, R2, then we have R3. And so now we have our voltages, and they're all going to be hooked up to a common terminal. So here we have R3, and then R2, and then this is all going to be hooked up to our integrator here, the inverting amp. And so now that we got them all connected, then this one is hooked to ground, the positive. What is our output voltage going to be? Our output V out. So this is our feedback resistor, remember, because that's on the feedback loop here. It goes from the output back to the input. That's why it's called R of F, output to input. And so the inverting summer, why I like calling it the inverting summer, is it's going to take the invert of each voltage that's input. So -V1, and then it's going to be R of F over R of 1. And so if you look at the loops in particular here, what you're going to notice is that this is falling along, this one right here comes from this one right here. And so if you just look at that one, cross out these R2, that's just like the inverting amp we did. And then you sum the next one with it. So you sum the next two. And so you look at each one individually. So here, we're going to look at the next contribution. So minus V2, R of F over R2. This one comes from here. Looking just at this one source individually. And then finally, the last one here, minus V3, R of F over R of S. And this one comes from this last one here. And that is your 3, and that's how it inverts. It basically inverts the input voltage, which we see here by the negative sign, negative sign, negative sign. That's inverting each of them. And then it sums them together because it's a contribution of all them combined, summing them all together, all their individual contributions to produce your output voltage. So I find that better than his explanation because I find it matches more the name of it for the inverting summer. And then the one pole transfer function. So this is the other one, the one pole transfer function. So how do we get this? Basically, this is going to have our input voltage. So I'll just represent that input voltage here because we only have one source. And then here's our R of S. And then we have our R of F. And then we have our capacitor here. And then this is hooked to the negative terminal. You'll notice all these op amps were hooked to the negative terminal for the input voltage. So they all had an inverting characteristic. And then we'll have our output voltage here, V out. So this is C of F. This is R of F here, and this is R of S. And so what we need to do is to get our transfer function, which is H of S equals, and remember, that's always the output over the input voltage. And we proved that for our devices that we're working with, since this is an inverting because it's hooked to the inverting terminal, it's negative ZF over Z of S. And we're going to see that our Z of S is given by R of S here. And then our feedback impedance is given by the parallel combination of these two here. So it's going to be because now we're dealing with specifically the frequency domain, it's 1 over S to C in parallel with R of F. And when you do this relationship, what you're going to notice and receive in the end is you're going to get R of F and then over RI, RF, a C all over S plus 1 CF R of S. And then what you're going to do is the exact same thing is where you're going to put this as an A, or sorry, B, and then this one as an A. And why is it called one pole then? It's because this is B over S plus A. And remember, when we're doing pole analysis, that's going to be when our denominator set equal to 0. And so there's going to be one value of S that's going to make this denominator go equal to 0. And so that's why it's called one pole, which I find more important. So as long as you understand the inverting amp, how this one works, this equation, literally, you can build the integrator from it because it's just putting in a capacitor in a resistor for your Z of F and Z of S. Here is just summing all the contributions of like 3 inverting amps, you can think of this as. And then here, it's the exact same thing, you just do the parallel combination of the two. And you'll get a one pole transfer function. Okay, now that we covered those devices, let's do another example. And so we need to find, this one is going to be the system over here. So let me do the voltage source, Vs of t. And then let me do a resistor, 1 ohm. And then we have 1 ohm. And then 1 farad. And here we have a 1 ohm. And this one comes in here. Dot negative, positive. And then this is our output voltage. And here we have this connected to a capacitor and something hooked to our positive terminal here. And so what are we going to do when we see this? It says determine basically the transfer function. And so when we're looking at this specifically, our transfer function is always given by, so find the transfer function. Remember, it's the transfer function. So it's H of S is equal to V out of S all over the input, which is right here. It's going to be V and then in of S. And so basically, what are we going to do? Well, I just noticed this was given to us in the time domain, this circuit, right? So we have to convert this into the frequency domain to get our transfer function. And so what we would have to do then is this voltage source here would become Vs of S, and then the resistor stays the same, resistor stays the same. The capacitor will now become 1 over S is C, since there is no initial condition provided. So 1 over 1 farad, that's just 1, right? So it'd be 1 over S. This would become 1 over S. Still 1 ohm, 1 ohm, 1 ohm. And then we have this hooked to the positive terminal. Here, one hooked in the inverting. Then we have this output voltage here. Okay. So the input voltage isn't hard for this transfer function. It's literally just the source here. Still same thing, voltage on the source. But the output voltage, that's the hard part, what we have to find. And so what we're going to have to do basically is for this one, you would have to find the voltages at each terminal in the gain. So when I'm looking at this one, the voltage at the output is going to be for V out, it's V1 over S. V1. Okay. This is hooked. We know if we're doing our circuit analysis, what I would say is, remember you define the essential nodes, which are connected to 3 or more elements. And the one, you make one ground. And so this is our V of N here. This is our V1, I'll call it. And so what I'm going to do now is I'm going to draw currents basically going into each of these. And so here, this current would be going in here to this node. This one would be coming back out. This one would be going downwards, and this one would be going to the right or something like that. And so for our V1, what we could say is we can make our specific one, what it's going to look like is we're going to have V1 minus, or sorry, where's this arrow starting? It's starting from Vs actually. Oops. V of S, and then minus. Then it's going to go to V1 all over 1 ohm. Plus, what else is coming into the node? This one right here, which is V out, it starts at that arrow and it goes to V1. So V out minus V1 all over, the resistance in between. And then what we're going to notice is it's going to be a minus for the next one since it's going downwards. And so it starts at V1, goes to ground all over 1 over S, what the impedance is in between. Then our other one is going out of the node. So I'm going to make it with a negative sign in front. So it'd be V1, it starts at minus, and then V of N all over 1. Set that equal to 0. So that basically just represents our currents here. This arrow is represented by this one, the voltage over the impedance. This arrow is represented by the voltage over the impedance. This arrow is represented by the voltage over impedance, and this arrow by the voltage over the impedance. Set it all equal to 0. Okay, we need to make another equation. And so that would be for V then. So there's going to be one current arrow coming down, one going in, and one going to the right. So our V of N, basically the one, we'll start from the top arrow. V out, it starts at, and then goes to V of N. So V out minus V of N all over 1 over S. And then this arrow is coming into it as well. So plus, where does that arrow start at? It starts at V1 minus Vn all over what's in between 1. And then our next one, remember, this current's almost 0. So it's going to be 0. So plus 0 is equal to 0. And so now we defined all the currents in particular. And right here, we're going to notice, isn't our V of N equal to 0? Because the voltage at the positive terminal is 0 volts, it's at ground. In V of N, recall, V of n is approximately VP, right? And so what we're going to see here is V of n will be 0. So remember I had n, it was to 0, 0, and 0. So now I'm just left with 1, 2, 3. 3 unknowns. Our voltage source, they tell us the unit step response later on. And so I'm going to assume if it's the unit step response, that means that if V of S is the unit step response. So we can actually solve the circuit if we actually know the voltage provided. So if it's the unit step response, remember, U of t in the time domain is going to be 1 over S in the Laplace domain. So that means this voltage source would be 1 over S. So I could substitute in for my V of S here. And my V, that's the only one, I believe, where we actually use V of S. And so this would be 1 over S. So if we rewrote this equation down here, we would have 1 over S minus V1 plus V out minus V1 minus, and then it'd be SV1, and then minus, and then V1 is equal to 0. Then this equation, if we rewrote it, we would get V out, S times V out plus V1 is equal to 0. Okay, so now we only have 2 unknowns, V1 and V out. And so we want to solve for V out, right? That's what we're trying to determine what the output is, because we know the input. We just need to determine the output. And so the output voltage here, if I'm trying to solve it, I'm going to see V from this equation right here. I can say V1 is equal to negative SV out. So now I can plug that in for V1 up here, given this information. So I can use this equation and plug it in for V1 here, V1 and V1, V1. Okay. Now that I got that, let's plug in. So substitute, woohoo! Substitution. So if we substitute in there, we're gonna have is 1 over S, and then minus a negative, that become plus S V is 0, plus V is 0, and then plus S V is 0, and then this would be plus S squared V of 0, and then this one would become plus S, and then it'd be V0 is equal to 0. Okay, so now we got it in this format. And so now what we need to do is we need to get the V outs all together. So V out, and then what I see here is we have an S squared. This term is going to combine this term with this term. So plus 3S. And then here I just have this term, V out, so that's 1. I don't see any other constants. So plus 1 and equals negative 1 over S. So V out in it's gonna V out of S will equal negative 1 all over, and then it's gonna be S times S squared plus 3S plus 1. And so that's how I got my V out of S. Now that I got my V out of S, I can plug that back into our transfer function finally. And so I'm gonna plug that in up here. So I have negative 1 over S, and then it's S squared plus 3S plus 1, then all over 1 over S. And so now I'm going to write this over here. It's going to be negative, well, this is a fraction divided by fraction, so this S will come to the numerator and cancel with this S in the denominator here. And so that will be my H of S is equal to negative 1 all over S squared plus 3S plus 1. So that is my transfer function that I found for this circuit, given that the voltage source is a unit step. And so that is how we found that. Our pole zero locations, if you were to find them, we would say that there are no zeros, but there are poles if you were to find out what the roots of the denominator were. Because remember, when you find poles, I'm going to make a side note here. Poles are when you make the denominator equal 0. And then zeros are when you make the numerator equal 0. And that's because when you have your h of s transfer function, I'm going to just write this as a side note on top. It's usually equal to, and then your numerator, like n of s all over d of s, your denominator. And so these are your zeros when the n of s is equal 0. Whatever value of s makes that numerator equal 0. And then your poles are when your denominator is equal 0. Okay. Now, we were able to solve this complex circuit, convert it into the frequency domain, find the transfer function, and then actually get an answer for it. So good job. We got that done with. And now we're going to talk a little bit about systems afterwards. So let me put that aside.
Wait, Brian, could you move that paper down a little bit?
Oh,
Just so I could take a quick pic, the bottom part. Hurry the fuck up.
got it?
Got it. Thank you so much.
Okay. Now we're going to talk about multiple system configurations. Multiple system configurations. So here, the first one is cascade systems. So cascade systems. And so this is when I have an input like x of s, and then it goes through h1 of s, then it goes through h2 of s, then produces an output like y of s. So they are in cascade, they are in series with one another. And when this is in series with one another, what we're going to realize is that just like we did before, because this isn't h1 a t and h2 a t, it's not convolution. It is actually multiplication. Because if you remember, this is just like a little flashback. Remember when we had x of t, then it was h1 of t? Just be careful when you're working the frequency domain versus time domain. And then y of t, you have to be careful because in series, this is the equivalent is h1 a t convoluted with h2 a t. That's the equivalent for those in series for x of t and then y of t. However, we're dealing with the frequency domain right now. So this is h1 of s multiplied by h2 of s. Because remember, convolution becomes multiplication in the frequency domain. That's a big thing to pick up on. And so this becomes y of s and then x of s. So that's the big thing about cascade is you multiply both of them. h1 of s multiplied by h2 of s. Next one is parallel systems. So parallel systems are when we have basically our x of s, and then we have h1 of s, and then we have h2 of s. So what's going to happen here is we realize that when they're in parallel with one another, they're going to add. And so the nice thing about when they're in parallel is they have this add symbol always. So what you do is I always think, oh, the equivalent block is always going to be h1 of s because it just tells you right here by the add symbol added with h2 of s. So there's no need to memorize that. h2 of s. Okay, and this produces our y of s. Okay, now that we have that, we need feedback systems. So feedback, what we're going to notice, what is it going to give us? So it's like here, let me just highlight, and in parallel, you add them together. So feedback, on the other hand, this is going to cause, basically, you'll notice the transfer function has a denominator in it, which is a little different than the other ones we're used to working with. And so for x of s, the reason it has feedback is, remember when we had feedback in an operational amplifier, and that feedback always went to the inverting terminal. So here that inverting terminal is replaced with the minus here. And so now we have this H2 of S, and then our other system is H1 of S here. And then it's going to go down, and then we have Y of S here. And so what's going to happen here is, basically, if we're trying to do an analysis on this one, we're going to see that, what's the best way to put this? When you do it, basically, just to speed things up, you already went for the derivation, but it's going to look like this in your denominator. It's going to be H1 of S all over, and then it's 1 plus H1 of S and times H2 of S. And then that produces Y of S. So that's the equivalent for the feedback system. And basically, because it's a feedback system, how you'll identify it is because of this negative sign right here. How you identify it's a parallel is because the positive sign where you're adding the two, and then cascade, they're in series with one another. So those are the three to be aware of and what their equations are. So have those down on your formula sheet. And now we're going to talk about basically how to do system realization. And so how can we make block diagram forms of systems? And so there's two ways you can do block diagrams from systems for, so I'm going to just say how to make block diagrams. I like that more than system realization. How to make block diagrams. So in an effort to make a good block diagram, what you need to do is basically, there's two different forms. So I'm going to talk about direct form 1. Honestly, I don't know why they called it direct form 1 and why they called it direct form 2. But so say we're given the system, it's H of S is equal to, and then here, we're going to have a B naught S cubed plus B1 S squared plus B2 S. Then in our denominator, we have S cubed plus A1 S squared plus A2S plus A3. Okay, so what we need to do for this one is you divide, so step 1, I guess, is divide the numerator and denominator by the highest degree of S. S. And so what you're going to notice, the highest degree of S in the denominator in particular, you'll mostly be dealing with proper functions, not improper. So don't worry about the degree of the numerator being larger than the degree of the denominator. But what we're going to see here is when we divide the numerator and denominator by S. So what's going to happen is we have our H of S here is equal to B naught S cubed plus B1 S squared plus B2 S all over. Then it's S cubed plus, and then A1 S squared plus A2S plus A cubed, or sorry, A to the 3 sub 3. Okay, now what we need to do is we need to divide by the highest degree of s, which is s cubed. 1 over s cubed, 1 over s cubed. So that would divide both numerator and denominator by the largest degree of s. And this is just like the secret form of 1 over s cubed all over 1 over s cubed. And so when we do that, we're going to get, as a result, what we're going to see is our numerator versus our denominator. What are we going to get for results? Well, when we see the numerator, it's going to become, if I divide this by s cubed, that becomes b naught, right? And then this one would become b1 over s. This would become b2 all over s squared. And so what we're going to see is this becomes b naught plus b1 over s plus b2 all over s squared. And then you're going to see this one down here. What's going to happen in our denominator? Well, if I divide it by the highest power, this would become 1 plus a1 over s plus a2 over s squared plus a3 over s cubed. And so, because remember, this is the denominator, so I separated the numerator from the denominator. So this would just be written in this form because s cubed divided by s cubed plus, and then a1 over s plus a2 all over s squared plus then a3 over s cubed. Okay.
Oh, Brian, I
So-
have a quick question.
Yeah.
Let's say the denominator is s squared and the numerator is s cubed. Would you divide everything by s cubed or just
You
the
will not
numerator
see
by
that
s squared
case
and the
because
denominator by s squared?
that is an improper, basically an improper function, and you will not see that.
So it'll always be like the same.
Yeah, it has to be proper in order to, you won't deal with that. Don't worry for the exam. Okay, so now that we got that, this one is going to be h1 of s. This one's going to be our h2 of s. And so what we're going to see now is if we're going to try and build this, how are we going to do it? And so I noticed, why did I choose h1 of s here and why did I choose h2 of s here? And so remember, this is your numerator. So just remember, this was your numerator. So that's why it comes first, you know, like you first write the numerator, then the denominator. That's how you can think of it. That's just a tip. Maybe that helps, maybe that doesn't. And so if I'm writing, this is my transfer function, remember? So we have an input. When you're starting your block diagram, always have an input. And then you're going to have something happening, and then you're going to get an output, right? And then the h of s is in the middle. Something's going to be occurring. We don't know what, we don't know how, but at least we can write it so far. We know something. And then what's going to happen here is this. Look at your 1 over s terms. First, we're going to do the numerator. We'll do h1 of s. Then you do h2 of s for direct form 1. And so what we're going to see is that this one here, it has a b naught for the magnitude. So we're going to have b naught. And then we're going to need to divide by 1 over s, right? So it's going to be, I need a 1 over s. And then this I can use to amplify by b1. And so I did my 1 over s times b1. Then I need another 1 over s here because we have 1 over s squared. And so I have my other 1 over s block diagram. And then we amplify by b2. Okay. So we got our 2 different configurations. And then we're going to notice it's the summation of all of them, right? So we have the summation of all these 3 terms. And so I need to sum them together. So here, the sum. And then here, we got the sum. Okay, so we got the summation of them. So we got this term done with. But now we need to get it with this term. So what are we going to do? Well, we need to write out our H2 of S, what that's going to look like. So our H2 of S, what we're going to see is that it's going to be formatted in the way such that from our output, how are we going to form our H2 of S? And so it's going to have to go through here. What we're going to notice is that this is just a 1, so we don't have to do anything for it. However, here's our first 1 over S term. If this was a constant, like 5 or something, then we'd have to take it into account, but it's just a 1. And so here's our 1 over S. And then we're going to have it in, you're going to see why I'm going to use a negative A1 here. You just wait a little while I use that. And then we have a 1 over S squared. Sorry. We have a 1 over S squared term, so just use 1 over S to get, because you have 1 over S and then 1 over S again, so that makes 1 over S squared. And then that's multiplied by A2. So minus A2. And then you have another 1 over S to get your final term. And so this is negative A3. And then you're going to combine these two. And why am I wanting to combine them in particular? And so then that brings an important question here where what we did in order to get specifically what we wanted is if you look at the derivation in particular of our H2 of S here, this format, we can see that H2 of S, it's going to be equal to our 1 over and then this large fraction down here. And so we can write this, let me see, what's the best way I can say? Let me pull up. Okay, so we had our H1 and our H2, right? They were multiplied by one another. They were in cascade with each other. We saw the H1 and the H2, they're multiplied by one another. When they're multiplied by one another, that means you can do them in cascade with one another. And so what we could say is this exact same thing. So let me just do this over here. We can do that our X of S is going to have to go through H1, and then it's going to go through H2 to produce our output. Okay, that's what we know right now because they're multiplied by one another. That means they're in cascade, just like we talked about before. And so since we know they're in cascade, I'm going to define basically this middle point here as Z of S. And so we know H1 of S will be equal to the output over the input. So H1 of S is going to equal the output, which is Z of S over the input X of S. And so that's where we get our B naught plus B1 over S plus B squared, B2 over S squared. And so our Z of S, if we solve for that, our Z of S is going to equal, and then it's going to be H1 of S multiplied by X of S. That's what we know. And so our Z of S, if we substitute in what we have in particular for H1 of S, what are we going to see? And so our Z of S is going to be equal to, and then our H1 of S is this B naught, so it would be B naught times X of S plus B1 over S times X of S, then plus, and then B2 over S squared X of S. And so you found what your Z2 of S is. So this is after it goes through H1 of S, which we just made here. So that means right at this point here, after we sum it all together, this point is Z of S. He is right after we did H1, which was given by right here, H1 of S. The output over the input is going to give us H1 of S. So this is our Z of S right here, which we found the equation for. And then we're going to try and find how can we make H2 of S to use it in order to make sure we get the correct block implementation for H2 of S? Well, look back here, right? We found H1 of S by taking the output over the input. Well, here, the output over the input will give us H2 of S, right? So H2 of S will equal the output, which is Y of S, all over the input, which is Z of S. Okay, now that we've done that, we need to substitute in what we have in order to get the equation in terms of Y of S, because now we have to build Y of S. Here we were building up to Z of S for our output, but here our output's Y of S. We need to build this in terms of Y of S. So Y of S is going to equal H2 of S times Z of S, okay? And so if we're going to do that, what I'm going to get is our H2 of S is given right here. And then our Z of S is given over here. So let's just substitute in, because we know our Z of S right here. So we don't need to substitute in for Z of S. But we need to find out what H2 of S is right here so we can get Y of S. So our H2 of S is going to be, when we put this in particular, our H2 of S was all of this. And so our Y of S will equal, and then this will be 1 over 1 plus A1 of S plus A2 of S squared plus A3 S cubed. That's our H2 of S, and then multiplied by Z of S. And so how can we produce this in a format that would be acceptable so that we can make sure this would look good? So what I would say is right now, in order to get this, our Z of S, we can't just write Z of S like all over this specifically. We have to write it in terms. So give me a second real quick. You would have to do your Y of S. And then if we multiplied, or I guess if we divided this onto the other side, what you're going to see is it's going to then become 1 plus A1 over S plus A2 over S squared plus A3 all over S cubed. And then that's going to be equal to Z of S. So we got it here in better terms of Y of S. So here we have Y of S plus, and then Y of S times A1 over S plus Y of S times A2 over S squared plus Y of S A3 over S cubed is equal to Z of S. Okay, now we got it in that format, but now we need to put it all in terms of Y of S here. In what we're going to use is, you're going to see is I'm going to have Y of S equal to the Z of S minus A1 over S Y of S minus A2 over S squared Y of S minus A3 over S cubed Y of S. Okay, so now we got it in terms of Y of S, but now we have some Y terms over here. And that was the only way so that it wasn't a weird fraction over this huge fraction, because we don't know how to do that. We can implement this, however, and you're going to see why I was using these blocks here. So I had my over S and then my A1, and right, this is connected to my Y of S. So it is my Y of S, the 1 over S, Y of S, and then negative A1 over S, Y of S. Here's my negative A2 Y of S over S squared, and then here's my negative A3 Y of S over S cubed. And so the only other thing here is our Z of S. And what you're going to see is if we need to add our Z of S into this, so I'm going to have our Z of S is going to come in here. So just like our Y of S was here. So this all needs to be summed together. So this would be our summation of this one here. We need to sum this one here and this one here. So this one would sum up here, then it would sum up here. So we got a summation of everything. So here's our H2 of S. And so we found this via basically what we had to do. Let's recap direct form 1. The biggest thing to remember is you divide the numerator and denominator by the highest degree of s in the denominator. So the highest degree of s in the denominator was 3. So we divided it by, we multiplied by the secret form of 1, which is 1 over s cubed divided by 1 over s cubed. We got our numerator, and we got our denominator. We make our numerator h1 of s. Numerator comes first, so think of that. It gets the first one, and denominator comes last when you write it. So that's why we got h2 of s. And so now that we got that, you can form your h1 of s basically using this little format here. We notice that they're multiplied by one another, so we can write it in cascade. And so that's the big thing to take away. You can write a cascade diagram for these. And so once you write them in cascade with one another, define a middle point as z of s. Use the function, the transfer function will always equal the output over the input. So output over the input, and then substitute, we need to solve for z of s here, our output. And so you reconfigure it and you substitute in what you know for h1 of s. To get h2 of s, you do the same thing, output over the input. And then you do y of s is equal to, you solve for your output. And then we notice here, it gave us this really big fraction. So we multiply both sides by this fraction here. And so what happened is then we were able to solve for y of s, but then here we had some terms still with y of s in them. So we had to define our integrators here with y of s connected to the output. And then we used our z of s also as our input, but then that's where z of s was right here. And then our negative y of s over s multiplied by a1, and then our negative a2 y of s over s squared, negative a3 over y over negative a3 s all over s cubed times y of s. So the biggest thing is know this step and know to make this diagram after you get, once you make this diagram, just do output over input and solve for both. And that's how you can make your block diagram. Okay, now that we talked about that form, we're going to talk about form 2. So I might keep that nearby. Is direct form 2 is a very similar process. However, you're going to notice that you're going to switch up basically the order of how they appear. And so what you're going to see is for direct form 2, let me put that here, direct form 2. Direct. Okay, so for this one, what you're basically going to see is you're going to switch the order of h2 of s and h1 of s. So that's what I'm going to write over here is switch order of h2 of s and h1 of s. And so what I like to do is basically you'll have your x of s. Just looking at the block diagram, I feel like is more helpful than memorizing steps for this format. And when I draw this, you'll see that there is a sharing of blocks basically on these integrator steps. But if I were to make this one, flip it so it came over here, so I'm just redoing this h2 of s up here, I'm literally just copying it and putting it down here because I'm switching the order. So I'm just copying everything I have here. So 1 over s. Then I have another 1 over s. Then I have another 1 over s. And then I have a negative a1. And then here I have a negative a3. And so you can see I literally just flipped, let me try putting these side by side. I just moved it from, this is direct form 1, and I just literally moved it over here. So just moved H2ves over to the input instead of on the output side. And then, so this is my H2ves. And then what you're going to notice is if we do H1 of S, which was right here on the other diagram, you'll see that there are already this 1 over S, this 1 over S, that's already there. We just need to add in these B0, B1, and B2 with the summation. So the 1 over S is already designed. All we need here is our B0. All we need here is our B1. Now all we need here is our B2. And then sum them together. And sum them together. And then this will lead to your output Y of S. Okay, so that is basically the little, how you form direct form 2. You form it from direct form 1, and then you just switch the orders of H2 of S and H1 of S. And so that's how you get it. And you notice that they share blocks. So direct form 2 is more of a condensed version. It uses less blocks. So the main thing is just switch the order. If you know how to get direct form 1, it's pretty easy to find direct form 2. And so now that we got that, let's look at this one. Might be a little weird how it's termed. So it gives you a transfer function. So let me do another example. It says the transfer function is this: H of S is equal to S squared plus 17S plus 20 all over S times S squared plus 6S plus 5. And it says use parallel realization. And we never seen the words parallel realization before. So that's a little scary. You're like, what's parallel realization? Basically, what that means is partial fraction expansion. So if you see parallel realization, it's just partial fraction expansion. So that's just the synonym for it. So don't freak out when you see that term. And so what we're going to see here is if you use partial fraction decomposition, you would get for your transfer function H of S, it would be 4 over S minus 1 over S plus 1 minus 2 over S plus 5. And so if you had to draw the block diagram, if he asked you for a block diagram format, remember, you always have an input and you have an output with your block diagram. That's the first place to start. Then you have all these three and it looks like they're summed together. So they're going to be summed together. And so one's going to be 4 over S, one's going to be negative 1 over S plus 1, and the other one's going to be negative 2 over S plus 5. So you're going to have these three blocks. And here. And then here it's going to go. And so you're going to have a positive, a negative, and a negative. And so that's going to form your Y best. And so that would just be parallel realization. It's a pretty simplified term for just partial fraction expansion. And it is a very simple block diagram here. It doesn't include like the gain and the 1 over S blocks where you have to use them individually. It combines them. And so that will sum up Laplace transform application for circuit analysis. So we're going to go over now to the next unit, which is going to be focusing on our Fourier series. So everyone's probably like, I do not like that unit at all. So how do you do Fourier series? And so let me switch it. Fourier series, how do you do it? Okay, so let's just look at it real quick. And so basically your Fourier series, it's going to be used for periodic signals. That's the big thing. Used for periodic signals. It's a big thing to look out for. And so for that periodic signal, you got to remember that the fundamental period is the smallest period. And so your fundamental period is given by T naught. And that is, so I'm just going to write it here, the smallest period you can have for your waveform. And then you're going to have the fundamental frequency, which is just, I'm going to use omega naught is your fundamental frequency. You'll see why. So how you can find one from the other is omega naught is equal to 2 pi over your fundamental period. And so what we're going to do is we're going to see different representations of our Fourier series. And so what we're going to see is for the Fourier series, when we have the exponential form can be used for any signal. So I'm going to say number one is our exponential form. And the main benefit is it is used for any signal. If it's real or if it's complex, it can be used. And so the big thing about this exponential form is it's given in the format x of t is equal to the summation from k equals negative infinity to infinity, and then it's ck e to the jk omega naught t. And so what here we have is basically k omega naught, in this one, is the harmonic. And so the harmonic is at different frequencies of those fundamental frequencies. So it could be like 1 omega naught, 2 omega naught, 3 omega naught. So it's at each of those specific fundamental frequencies, it's multiplications of that fundamental frequency. And then the CKs here, those are the Fourier series coefficients. Fourier series coefficients. Those determine how much of the harmonic you're going to have. And so what we're going to see is that the coefficients can be found by specifically this form. C of k is equal to 1 over t over 1 period of x of t e to the negative j k omega naught t dt. And so this is just over 1 period. You can use this relationship to find your coefficients. And the coefficients are going to tell you how much of that specific harmonic is in the signal. And so that's the big thing, is the coefficients will tell you how much of that specific harmonic is in that signal, and you sum all the harmonics together in order to get the output signal desired. And so what we're going to have here is, let's do one example. And so our example is going to be the waveform here. So let me get my ruler. Oh, I can just freehand draw it. Okay, so here we go. And, oh, sorry, let me move it up. We have, it goes up to 1, and it's going to be an exponential waveform. I think something like this. DK, it's going to go up, DK, up, DK. Okay, so it's going to be -2, 0, 2, 4, 6. And so what we need to do is parse. What we're going to see is we have this signal here, and it gave us, it's e to the -2t. That's the signal we have. So what is our specific values we should get for the Fourier series coefficients? If it says find the Fourier series coefficients, how would we approach this problem? And so if we need to find the Fourier series coefficients, that's going to be C of k is equal to, remember, 1 over t over 1 period x of t e to the negative j k omega naught t dt. And so this is going to be over 1 period. And so a period we can see is 2. And so it's going to be 1 over 2 from 0 to 2. That's over 1 period length. And then our x of t is e to the negative 2t. And then e to the negative j k. And then here we have omega naught t dt. And so what we're going to see here is basically we're going to have our format. So when we write this, can't you combine these because they have the same base? They both have e. So you can write it as 1 over 2, 0 to 2, e to the negative 2t minus j k omega naught t dt. Because they have the same base, you can add exponents. And so what we're going to have to do here is we can redo it so that we can get the t term common to both. So we just get a constant for the others, because t is the variable of integration here. So we need to take out a t from both terms. So if I do that, if I have my negative t, then I'm going to have 2 plus jk omega naught dt. And so this part here is all a constant, right? This is constant. So what's going to happen is when we take the integral, it's just going to be 1 over and then 2 plus jk omega naught. And then it's going to be a negative sign in front just because that e to the negative t. And then 1/2 out here multiplied by all that. And then e to the negative t 2 plus j k omega naught. Then it's from 0 to 2. And then we have what our format's going to be for CK is for t, we need to plug in 2, and then we'll evaluate and then also plug in 0. So it's just a simple integral now. And so we need to follow what it says. For a specific value of omega naught, you're going to realize that omega naught, that's a constant, remember? Omega naught is 2 pi over t. And our period is 2 seconds, so it's 2 pi over 2. And so omega naught is just pi. So I can plug in here pi and pi. Makes sense? So when I go to do the actual substitution in here, I'm going to have negative 1 over, and then it's 2 plus j, and then k pi, e to the negative, and then 2 in for t, that's what I'm substituting in, and then 2 plus jk, and then for my omega naught, I found out was pi, and then minus, and then a negative 1, so that would just become plus here. 1 over 2 plus jk pi, e to the, and then it'd be e to the power 0 because I'll plug in a 0 here, so everything becomes 0, and that's 1. And so we're going to get, what we're going to see is if I multiply this through by, let's see, what would I do? Minus plus 1. So if I take out, this term's common to both, right? If I take out a negative, or wait, what should I do? Take out the, yeah, 1 over 2, and then multiplied by 1 over 2 plus jk pi. That's common to both, right? And then it'd become e to the negative, this 2 would distribute, so it'd be negative 4 plus And then, oh, sorry, that -2 distributes both, so it'd have to be minus. -4 minus, and then it'd be 2 pi jk, and then plus 1. And so then here we have 1 minus e-4. Okay, what we can say from here is I can say 1 over, distribute this 2, so it becomes 4 plus, and then j 2 pi k, and then e to the -4, and then here, this e to the power of -2 pi jk. Well, remember, k is a constant. It's because we're dealing with k, it's going to be like 0, 1, 2, 3, 4, 5, So 2 pi times 0 will give you 0. And then if we're going to see what else is going to happen, if we have like 2 pi times 3, well, that's going to give you 6 pi, right? And so 6 pi, remember, this is your phase angle. If you're going to have your phase angle, it's going to be 0. And so what you're going to notice is this term, e to the power of 0, it's going to be just 1. And so that'd be multiplied by 1. So this term right here, because of e to the -2 pi jk, if you plug in k0, that's going to give you e to the power of 0, which is just 1. And then if you plug in 1 for k, that's going to give you e to the power of -2 pi j. But remember, e to the -2 pi isn't that the same -2 pi as the phase angle 0. So it's going to just be e to the 0, which is 1, because this is your phase angle, remember. And so it'll give you e to the -4 and then plus 1. That's what you would get here in particular. And then, so we have this, let me see, did I get a minus sign? E to the negative. Oh, I just forgot this minus sign in front here from this one here. So it would be negative. Okay, so then here we got our answer here. And so this one, if you were to find the magnitude and phase, which you might be asked to do, what would you do? So you have to find the magnitude and phase. I would say that this is our CK, remember? So let me just rewrite it. So our CK is equal to 1 over, and then 4 plus j 2 pi k. And then it would be 1 minus e to the -4. So our magnitude as C of k is going to equal, and then it's going to be 1. So here we have the magnitude of the numerator we have to do and the magnitude of denominator. Well, isn't 1 minus e to -4? That's just a number, right? Because 1 minus e to the -4, that's just a number, 981 point something milli. And so here, the magnitude of the numerator is just going to be 1 minus e to -4, because if you take the square and then square root, it's the exact same number. And then denominator, though, you have to take the square root of 4 squared plus, and then remember the complex term, it's just going to be 2 pi k squared. And then if you have to distribute, you got 1 minus e to -4 all over 16 plus 4 pi squared k squared. Okay. Then your angle C of k, what's that going to be equal to? It's going to be, remember, tan inverse the numerator. Is there any imaginary term in the numerator? No. 0 over, and then the real part would be 1 minus e -4. And then your denominator would be tan inverse. And then it would be of your imaginary term here is 2 pi. all over 4, right? 2 pi, oh, k, sorry, all over 4. And so what you would have here is, well, your numerator, it travels 0 in the y direction and it's positive in the x direction. So that's going to be along the real axis. So degree 0. And then here, you're going to have tan inverse of pi k over 2, which this we're going to see. So you can write your angle as 0 minus tan inverse of pi k over 2. So that's how you'd write the numerator, the magnitude in the phase part. And that is how you would solve it. So the reason we were dealing with, let's see, this one is we did have an imaginary part to it. We could see with our J. And so since we had an imaginary part, that's why we dealt with the exponential format. Now our next form is going to be the cosine and sine, or the trigonometric form. And so what we're going to notice, okay, real quick, before I dive into that, I just want to say something on the exponential form. So let me go back here. Because we're going to see that we took a signal, our x of t here, right? And this was continuous. It had a value at every point, right? This is our x of t, it's in the time domain. And what we see is in our answer, it is going to be discrete because it's only for values of k, which are 0, 1, 2, 3, 4. So what the Fourier series does is the Fourier series takes a continuous time signal, which is like given by x of t, and converts it to a discrete signal. And so what we're going to see is we're going to get like x of k, or you can write it as c of k, or oftentimes they just say c of k, but you need to pick up on the fact that that's a discrete signal to look out for. And so now that we got that, we'll notice that since c of k, it deals with sometimes complex values you'll have, like complex signals. And so c of k may be a complex number. C of k may be. And so since it might be a complex number, it has Hermitian symmetry or conjugate symmetry. Because remember, complex values, they have a conjugate. And so that's why we like to say Hermitian symmetry. So conjugate symmetry. Biggest thing to take away from this is just to realize that c of k is equal to c minus k. So that basically means that the conjugate is equal to the negative value of the complex, or of the value for c of k. The negative value of the c of k is going to equal your conjugate. So you're going to notice that the magnitudes have even symmetry, as in Hermitian symmetry. So the magnitudes here the conjugate is going to have the same magnitude as the negative value of the signal, and it have the same value also as the signal itself. But the phases, so the magnitudes have even symmetry, but the phases have odd symmetry. Where you have your c of k is equal to c of negative k, which is equal to c of k. So phases have odd symmetry. Phase has odd symmetry. And so what we're going to notice is that this is pretty important when you have Hermitian symmetry for conjugate symmetry, when you have to do its graph. And the reason why is when you graph this, it's basically going to show you for negative values of k. So this would be your positive k's, and this would be your negative k's. And say you're graphing the magnitude of c of k. So the magnitude of this one on this spectrum, on the positive side for the positive k, is going to equal the negative k's magnitude. And so it's symmetric, it's even. But the phases, what you're going to see is they're odd. So for when you have your phase angle c of k, you have your positive k's on this side, have your negative k's on this side. You're going to see if I have one down here, it's going to be here. One down here, it's going to be here. One down here, it's going to be here. And so it's odd symmetry. And so that is an important thing just to take away when you have your k values. The negative value k is odd for your phase, but for the magnitudes, your negative value k will be the same as the positive value k. Okay, now we got that. We need to do the sine cosine form, or so the sine cosine, aka trigonometric form. So if we have this, the sine cosine form, it's basically going to tell you that you're going to have your x of t equal to a naught plus then the series from k equals 1 to infinity of a k cosine k omega naught t plus, and then the series of k equals 1 to infinity b of k sine k omega naught t. Okay, now that we got this, we need to figure out how to find a naught, a k, and b of k. And so here, what we need to do is our a naught is going to be when our k is equal to 0. And so that would mean basically for even signals, you have to find these coefficients, which basically here's one coefficient, here's another coefficient, here's your coefficient. This is telling you how much of the k harmonic, how much of the 0 harmonic. And so this is like your DC signal right here, because it's the 0 harmonic. At frequency of 0, that's a DC signal. And so that's what it's telling you right there. And so what we're going to see is a naught. It's going to be 1 over the period 0 to t x of t dt. A of k is going to equal 2 over the period 0 to t. It's going to be x of t cosine k omega naught t dt. And then you're going to have b of k is equal to 2 over t 0 to t x of t sine k omega naught t dt. And so now that you got that, you got the sine, cosine, and trigonometric form. And so what we'll notice is this is telling you how much DC signal you have. So this tells you the DC signal. Let me just write it here. DC signal. And remember, DC signals have even symmetry. And that's why we always consider it is the function even. Because remember, if you have a constant value, right, it's symmetric with respect to the vertical axis. Here, we have our, this is telling us how much of the cosine waveform you're going to have for your signal. This is telling you how much of the sine waveform you're going to have for xt. This is telling you how much of the even part and how much of the odd part. Because remember, you can always construct the signal from its even and odd parts. It's telling you how much of cosines do you have, how much of sines do you have in your signal. So these coefficients, this is telling you how much of the DC signal, how much of the cosines are in your specific signal, how much of the sines are in your signal. And you're going to see that the composition of those at the different multiples of the fundamental frequency, you're going to see how much that signal makes up your final signal. So your A naught is given over the area under the curve, and it's taken over the whole period to give you your DC signal. And then you're going to get your A of Ks, which correspond to your even signals, and your B of Ks, which correspond to your odd signals. The reason why here it is 2 over T is because it takes into account the positive and negative Ks and then the positive and negative Ks here. So it takes into account both. And so because you'll notice in this summation here, it's only in the positive. But there's harmonics in the negative region as well. So that's why it's 2 over T and 2 over T here. It's not 1 over T like this one, because this one just occurs at 0 frequency. And then this one can occur though at positive 2 and then negative 2, like something like that. And that's what we're gonna see. And what we need to take into account is relating this to the one we just had, which was the exponential form. So let me put that right above and see how they're related. Okay. Okay, so looking at these two and seeing how they're related, we're going to notice that the real part of C of K twice times the real part of C of K will give you your A of K, right? Because this is 2 times 1 of T, correct? 2 times 1 of T. So twice the real part will only give you the cosine part because this is a complex exponential and the only part that's real is the cosine part. So we're going to say that the A of K is going to be equal to twice the real part of C of K, where the B of K is going to be twice because it's 2 over T. So it's twice the imaginary part of C of K. And then A naught, that is going to be equal to C naught, because C naught would just be 1 over T, x to T, e to the 0, which becomes 1. So this would just be equal to C naught. And so now we know the specific conversions, but the main principles to take away is know these formats, just how to calculate those coefficients in the equations given for them. Yes. This formula, know it, know how to calculate those coefficients, know this formula for the sine, cosine, know those, and just know that. This just tells you how they're related, these two formats here. This part and this part here just tells you how they're related. Okay. Now that we got that, then we're going to see that C of K, if that's both the real and the imaginary part, right? So our C of K, if this is the real part of C of K and this is the imaginary part of C of K, then wouldn't you agree that your A of K, so if I wrote my C of K is equal to 1/2 A of K minus J B of K, it would be, this is basically telling us this is 2 times the real part. So in here, this would be 2 times the real part minus 2 times the imaginary part. So this would be your cosine part and your imaginary part. The 2 down here would cancel with the 2's here. So it would just become the real part of CK minus the imaginary part of C of K. Oh, sorry, I forgot a minus here. So then it just become, if you substitute this in, this would be 1/2, and then it'd be 2 times the real part of C of K minus 2 times the imaginary part of C of K. Right? And so this 2 would cancel the 2 here and the 2 here. So you would just get minus, and then minus, minus, so that become a plus. And then I forgot just the J term in here. So here we would see that it would become just the real part of CK plus the imaginary part of CK. And so that's how you form your CK. It's the real plus the imaginary. And so now that we talk about that, the third form that you need to be familiar with is the amplitude phase or compact trigonometric amplitude. And so to form the amplitude phase or compact trigonometric form, you're going to have, it's going to look like this, which is your x of t is equal to m naught plus, and then from 1 to infinity. And then it's going to be mk cosine k omega naught t plus, and then the phase angle of k. And so here, what you're going to see is that you're going to have your m naught is going to equal your a naught, which is going to equal your c naught. And so that is going to be your DC signal. So that's the repetition you saw from here, where you had your a naught, which was equal to c naught. That's the same thing here, where it's your m naught is equal a naught equals c naught. And then your next one, which is going to be your m of k, is going to equal the square root of your a squared, your ak squared plus bk squared. And then, so that's the twice times the c of k part if you're looking for the conversion. And then your phase of k is going to equal tan inverse of your imaginary part over your real part, which is going to equal the phase of c of k. And so this is your compact form. It basically just comes from your cosine and sine form. So you just write it all in terms of cosine. And then your phase angle, remember, sine is only 90 degrees apart from cosine. So it just takes into account the phase difference. So that's the third format to be familiar with. Okay, now that we covered all those three different formats, we're going to see example where we're going to have to determine specifically the coefficients of them. And let's start out with this one over here. So here's our example. And we're going to be given a waveform. So it looks something like, let me do one from actually the, does anyone have a particular example from the textbook, numbers 1 through 4 you want? Just drop it in the chat or say it out loud. If not, I will just pick one.
2.
Number 2. Okay. Let's look at that one. Okay, number 2. So it gives us the waveform here. And it goes from, okay. We have -4, -3, -2, -1, 0, 1, 2, 3, 4. Okay. And so now we know those, and we're given the waveform. It looks something like this, where it goes through the origin, goes. Okay, and then here it goes. Something like that. Okay, so the important thing is we got it. Oh, oops, wait, nope, it does not look like that. Ignore that real quick. We'll redraw that. Okay. So, and then it goes constant. Yeah. Oh, oops. And just ignore that part. We got this part over here. Okay, so this part is a repeating waveform. We're gonna see that particularly we will have, let's see, do I have a whiteout? No. Okay, just ignore this part right here. So we're going to see that this repeating waveform basically goes from the point, it's about like 1.5 and it goes to like 4.5. And then it's going to repeat itself. And so between 1.5 and 4.5, that's a period of 3. So I'm going to mark that here. So this is a period of 3. And so we know the period of 3, and it has an amplitude of 10, and it goes down to -10. And so the first thing off the bat, I would say, is this an even or an odd signal or a DC signal? And so the big thing is we see this isn't even because you can't just flip it over to the other side and get the same signal. But we see it's odd because you can flip it and then you can flip it again and get the waveform on the other side. And it's DC also because the area under the curve, which is given here, I'm just going to shade it in, would cancel out the area above the curve. And so that's why it is a DC signal. So we determine it's even, oh, sorry, it's odd and DC signal. So what I'm going to do is, I like this sine and cosine form just because that's simplest for me. And the biggest thing is I notice this is periodic. Periodic. And when you, I might have forgot to mention this, for the sine cosine trigonometric form, the big thing is it must be periodic. And for the amplitude phase form, it also must be periodic. Those are the big things to remember. So we determined what type of symmetry it has. We determined it was periodic. And so we're going to use the sine cosine form. And so what it is since it's odd, I know from that point, because it is odd, A naught and A of n equals 0. So we're only going to be finding our B events or B of K's. You can use N and K interchangeably. Some people like to use N, some people like K. And so you can use one or the other. And so we're only going to be finding our B of K's here. And the reason why A naught is 0, I'll just prove it to you. 1 over T over 1 period, X of T dt. Well, the area under 1 period, right? The area above the curve cancels to the area below. So this actually evaluates to 0. The area over 1 period cancels to 0. And then your A of n will equal 0 because you'll see when you do the exact same thing, there's no even part to the sample. So it will cancel out. But your B naught, sorry, your B of K is going to equal 2 over T over 1 period, your X of T sine of K omega naught T dt. Okay. And so what we need to know from here is our X of T within 1 period. So within 1 period here, it's from -1.5 to 1.5. And so I can do that for my integral, -1.5 to 1.5. And then 2 over the period is 3. And then our X of T, what we're going to notice, the big thing is when we're taking the integral, right, finding the area beneath the curve. But what I notice is, isn't the area from -1.5, which is like here, to 1.5, this is 0, right? And the area from 1 to 1.5 is 0, correct? And so what I'm going to say here is I'm going to rewrite my bounds and say up to 1 and -1, correct? Because it's just 0 area under those regions, so I don't need to include those in my bounds anymore. And then my X of T is given by, well, what is between those bounds? What's the line of this function? It's -10t. And then it's sine of k omega naught t dt. So take that out in front. So you got negative 20 over 3. And then from negative 1 to 1, t sine k omega naught t dt is equal to b of k. So we now know what we have for b of k's here. And with this knowledge, we have a linear and we have a trigonometric term. So that's going to be, if you remember Liotte, it was from Calc 2, but if you had to take the antiderivative, you make your u be the algebraic term, your dv equals sine k omega naught t dt. Your du equals dt, and your v is equal to 1 over k omega naught. And then, oh, remember cosine though, so it'd be in, because cosine, the derivative of cosine is negative sign, so that's why I put negative in front. And then cosine of k omega naught t. And then what we need to do here is format these ones here. And so what we need to do is we got our b of k. Let's solve this integral. So b of k is equal to negative 20 over 3. And then it's going to be here, do uv times v du. I say ultraviolet voodoo, that's how I remember it, uv v du, ultraviolet voodoo. Some people like it, some people hate it, I like it. So negative t over k omega naught cosine k omega naught t. And then that'd be evaluated from 1 to negative 1 minus the integral from negative 1 to 1. And then it'd be negative 1 over k omega naught cosine k omega naught t dt. And then here, you're going to see that negative 1 over k omega naught comes in the front. Negative 1 to 1. And then it'd be cosine of k omega naught t dt. And then this integral, if you evaluate it specifically at 1 and negative 1, you're going to get negative 1 over k omega naught cosine of k omega naught, and then minus, and then it'd be a negative 1 over k omega naught, and then cosine of negative k omega naught. So this becomes so closer, so negative 20 over 3. Okay. And you're going to see that, oh, sorry. So this will become, then once we get this format, remember cosine is an even function, so this negative won't affect it. So it's just going to become negative 1 over k omega naught cosine of k omega naught. Negative, and then cosine k omega naught all over k omega naught. And then negative 20 over 3. And then plus, and then 1 over k omega naught. The antiderivative of cosine k omega naught t is going to be 1 over k omega naught sine k omega naught t. Then 1, negative 1 to 1. And then here now we have to evaluate specifically our integral. Well, these two terms will combine, right? They're the exact same thing, have same denominator, and it's negative cosine, So it'll be negative 2 cosine k omega naught over k omega naught, negative 20 over 3 in front. And this term here has a plus 1 over k omega naught. And then it's going to be a 1 over k omega naught sine k omega naught. So 1 over k omega naught sine k omega naught minus. And then it'd be 1 over k omega naught sine of negative k omega naught. Remember, sine is an odd function, so this would come out and make a plus. So it actually becomes 2 over k omega naught sine k omega naught. and then plus 1 over k omega naught on the outside. Multiplied by that. And then we have a -2 cosine k omega naught over k omega naught. -20 over 30. Okay, now that we got that, all we need to do here is it's going to become 2 over k squared omega naught squared sine of k omega naught. And then we have -2 cosine k omega naught over k omega naught, -20 over 3. Okay, now here we're going to notice, oh, sorry, forgot the plus sign in between. It's going to become, well, if we remember what our omega naught is, and if we distribute our omega naught from the very beginning, remember our period, and write this on the side was 3. So omega naught will equal 2 pi over 3. So therefore we can plug it in here, 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 and here. So 2 pi over 3, we plug that into denominator. What's going to happen is it's going to be 2 pi, okay. And then the 3 is going to come to numerator, so it'll be -6 cosine, then 2 pi over 3, okay. Plus, and then 9, so that'll be 18 all over 4 pi squared, so 4 pi squared, k squared, then sine of 2 pi over 3k, then -20 over 3. Okay. And then here, what's going to happen is we have -20 over 3 times this. So if we multiply this out, what we're going to see happen is we're going to get 20 over 3 times -3 would be 60, because this would cancel this one. Right here, I noticed this would be 3. This would be then a 1. This would be divided by 2. So this would just be a 2. This would be a 9. Simplify. So this would become -60 cosine 2 pi over 3k all over, and then 3 pi, okay. Oh wait, this would be negative times negative, so that should be positive 60. And then here we have -180 all over 6, this looks like, and then pi squared k squared sine of 2 pi over 3k. Here we divide, so we get 20 cosine of 2 pi over 3k all over pi k. Here we have divide, and we're going to get 30 over pi squared k squared sine of 2 pi over 3k. Okay, now we got all that within our specific format for a formula. And now that we got that, remember our x of t is equal to our a naught plus summation. This goes back to the sine cosine format. It's k equals 1 to infinity. It's your a of k, and then it's your cosine of k omega naught t plus, and then your summation from k equals 1 to infinity, e of k sine, and then it's going to be k omega naught t. So here you're going to have your this term, remember, evaluated to 0. This term evaluated to 0 because it's only an odd. So it's going to be here what you're going to have as your format. So you're going to have 20 over pi k cosine 2 pi over 3k minus 30 over pi squared k squared sine of 2 pi over 3 k. And then everything is multiplied by, because remember, that was only our b of k term up here. Sine of 2 pi over 3 kt. There we go. And that is your x of t.
You shift the paper up a little bit, please. Thank you.
Like that.
Yeah, that's perfect.
Okay, so that is how you'd solve a sine cosine format. And then and then you're going to notice that they're going to give you different waveforms. Specifically, it's going to look something like this. We might throw these at you. Let me zoom in. Last time it didn't work too well. These waveforms are oftentimes associated with these functions. So here, let's see. Okay, yeah, but whatever, you can see the general shape. But these waveforms, you'll see them in like the ZY books, and they are associated with all these types of signals you might see where they're like, take the Fourier transform of this. And the most important thing is to notice that your coefficient term is given here, but this cosine term added at the end, that's because it's an even signal. And that comes from like that cosine, what we're dealing with before, where you have to multiply all that at the very end. You multiply it by that last term here. Same thing with this one. See how this is an odd signal? This sine term doesn't deal with the coefficients. It deals with multiplying at the very end of the signal. This, you can see, is an even term. So the cosine term at the very end, you multiply that at the very end, because right in front of cosine, this is how you find the coefficients. Then that cosine term you add at the very end. And then this would be like your DC offset. And then here, this one's dealing with same thing where it's an even signal. So this cosine term you multiply at the very end, but this is dealing with your coefficient term. So just make note of that your coefficient term is everything in front of this last part here, but also watch out for your DC term, which might be included in front of the sigma. These ones might look a little better. Okay, where this one is telling you basically, oh, if you see this waveform, the biggest thing, so if you see this type of waveform here, the biggest thing is when you see the equation for the Fourier series, you need to realize that the x of t is going to be equal to, and then here is the coefficient term ak, and then here is your, you multiply it at the end by the cosine. And so that was corresponding with how we have our sine cosine formatted. So at the very end, we multiply by the, see how we have it written. So you have the DC plus, and then your coefficient multiplied by the cosine. And then here plus the BK multiplied by the sine. Okay, now that we got all that covered, let's talk about Parseval's theorem real quick. So Parseval's theorem. Okay, so Parseval's theorem, oops, let me zoom out, sorry. Parseval's, what does that say? He basically stated that the power in the time domain is going to equal the energy in the frequency domain. So the power, which is given by 1 over t, from 0 to t, is taken over, and then it's the magnitude squared. You might remember this formula, you might not. It's going to be equal to, and then it's the summation of this magnitude of c of k squared. And k equals negative infinity to infinity. And so this is just saying that the average power of periodic signal in the time domain and the energy that's seen on the frequency domain are the same. And so the power in the time domain is equal to the energy in the frequency domain. And so that is a very important note. Notice that here, so just make sure this is power in time domain is equal to energy in frequency domain. Okay, so that's what Parseval said. And basically he was just going, that was cool part of his formula. You know, that's what Parseval did. That's what his contribution was to life. And so that's what that might be a little sad. Sorry, I don't want to be remembered for that. So basically, now that we know that, the things we need to watch out for is, remember our real valued signal when I said C naught is equal to A naught and CK is equal to 1/2 of AK minus J B of K. And so when we're looking at Parseval's theorem, specifically the power equals 1/t, and then it's 0 to t, and then it's x of t squared dt. It's going to be equal to, and then what we're going to see is the summation A naught plus the summation from k equals 1 to infinity. And then it's A of k squared plus P of k squared all over 2. It's basically showing you that within the Fourier series trigonometric representation, how we can find specifically the power using the format we know that for our C of k, how we can find it, but it's using what we know in order to plug into this equation. Based off all of our Fourier series representations, we can represent it this way in order to find the power. And so this is just telling you, it's basically the coefficient squared over 2 plus the coefficient squared all over 2. And it's just, oh, oops, sorry, I forgot for this. This is just telling you, remember, so if it's telling you for the power DC, because remember, this is your DC, so the power DC is equal to the amplitude squared. But for the power AC here, this is what the ZY books, I believe, is trying to get to you guys, is going to equal the amplitude squared all over 2. And then if there's another amplitude squared all over 2. And so this is just another way of representing Parseval's theorem. Basically just says that the power of a DC signal is equal to the amplitude squared and then plus, and then the amplitude squared, the AC plus the amplitude squared of the other signal. And so the average power is equal to the DC power plus the AC power. That's an easier way to understand what was in the notes. So it came off a little weird, I think, in the notes, but it makes more sense for the ZY books, I thought, in terms of how these were presented. This is just DC power and this is AC power, and how you should take those into account with amplitude. And then what you need to notice is that for the compact trigonometric form, remember we had like the M naught, and so the M naught is equal to C naught, and then we had the C of 1/2 of M of K is going to be equal to C of K, the magnitude. And so remember, because MK combines like the AK, BK, but if you take half of that, that just gives you the CK. And what you're going to notice here is it's literally almost the same thing, because remember, power by Parseval, 1/t, and then 0 to t, and then you take the magnitude of x to t and you square it, dt. That's going to equal, and then it's your m naught squared plus the summation from 1 to infinity, and then it's mk squared all over 2. Important things to realize here is your mk squared over 2. This is okay, this right here, same thing. Power DC equals A squared. Remember, this is just your constant DC term. Here, this is dealing with, remember, it's like the cosine of omega t plus theta. Well, this is your AC power still, because that's dealing with your cosine term, your AC term. That's just A squared all over 2. Okay. And it's just telling you that the average power is equal to the DC power plus the AC power. Okay, makes sense? Now, we need to do, what is the average power of this signal right here, where we have x of t is equal to 5 cosine 3t. Okay, well, what I would say is, okay, this looks most likely, it can be either trigonometric cosine sine form, or it can be compact trigonometric. When I'm looking at this in particular, I would say comparing it against the two, let's see which one. So if I was given this, would this be trigonometric here, cosine, and then I'm given the 3t, okay. Oh, I should have put like a 3kt, sorry. And so that's what I have here. And then, so this could qualify as trigonometric, but also my other way here, it doesn't have an offset, but it looks just like this format too. So it looks like both the amplitude phase, because the offset would be 0. But remember, it's the same exact thing. You just take the amplitude and you square it. So the amplitude here would be, this is an AC form. It's an AC form. So that's why you can take the amplitude, you square it and divide by 2. And so you get 25 over 2. That is finding the average power. So find average power, if it ever asks you for that. Another one would be, what if it had, for another example, if x of t equals, then here it would be like 3 cosine of 4k t plus 90 degrees plus 5 cosine, and then it's 5k t plus 80 degrees. Well, here you have two waveforms. They're both AC. You just take the amplitude squared, divide by 2, and you do that to both of them. So this would be 9 over 2 plus 25 over 2. And that is 9 plus 25, that is 34 over 2, which is 17. There you go. And so now that we got that, basically, we can get a little into the truncated Fourier series and why you might see that. Okay, so the truncated Fourier series, what you're going to notice is this is approximating x of t, because right now when we use these formulas, you know, like we went to infinity, and then here on the other side, it's from 1 to infinity. So like, however, can you store infinity in your computer? No. And so the biggest thing is what they say is that we approximate it only by like n terms. So it might go up to m only. It doesn't go up to infinity. And so what they write here for the error of approximation, what we're going to see is our, what ideally it is it's x of t equals the summation from negative infinity to infinity. And then it's ck of e to the jk omega naught t. Okay, that's what we're used to seeing it as. However, what's going to happen is basically we approximate it, and we take this into account by using the error of the approximation, because we can't go from negative infinity to infinity in our calculator. And so what we're going to do is our error signal, it's going to be given by a specific value. So we're going to go k equals some integer value up to some integer value. And it's going to be dk e to the jk omega naught t. So our error is going to be the discrepancy between the real valued signal, what you should get, versus, so the ideal signal minus what your computer can handle, because your computer can't store infinite terms. And so now that we got that, we have the summation. So here it's going to be from negative infinity to infinity. And it's going to be negative ck e to the j k omega naught t minus. And then here's the summation from k equals negative n to n. And then this is going to be what our computer can handle, d of k, then e to the j k omega naught t. And so here, what we can do is we can write it specifically. These are like bases, right? And they're going to include, let me see. This basically just tells you the amount of air signal here, but they can go on, but the notation gets a little heavy, but I feel, let me double check this real quick. Okay, this says that, okay, yeah, this is the correct format. From negative n to n, they share that, right? Both of these share those because this one's limited between n to n, where this one goes from negative infinity to infinity, but they both share n to n. It is going to be ck minus dk. I don't know where this negative sign came in from, sorry. I'll just make that positive. But it'd be ck minus dk. And then it's going to be ck minus dk. And let's see, and then the other term, let me just write that for now. It would be for k, which is greater than n. And then this would just be c of k. Let me loop. Okay, which would be ck minus dk, then e to the j k omega naught t. And this one would be ck e to the j omega naught t. And so what we have here is basically, it is saying that the amount of air signal we have is going to be, this minus this will go to 0, right? Because the only thing, if they are exactly the same, because they'll calculate the same values for these values of n, this should be 0. Whereas this will tell you the actual air. And so this is going to be where we get the actual air from. And so let's see, what do we eliminate? That one, what do we make it the C case good? Okay, so then when we write it particularly in the format for our power signal, what we're going to see, because this is the only part from the air that exists. So this is what we're going to see for a specific air. And then when we do power, remember it's 1 over t, and then it's over 1 period. And then here's going to be our air signal, and then squared dt. That's going to equal, well, we noticed this one canceled, but this term still stayed alive. And remember, power is amplitude squared. And since the C of K, is that dealing with, let me check real quick, is that dealing with C of K here? Because that would be an AC term. Let's see real quick. Okay, he has it written as, he says that the actual summation for K is greater than N is going to be, okay, this is our amplitude, right? It's in front, it's the coefficient. So we're used to power, it's C of K squared. And then what's interesting to me, I don't know if you guys know why, but this coefficient here is in front of a sinusoidal. So I feel like it should be divided by 2. But he just left it this squared, which that follows the format of DC. I don't know if anyone knows here why he didn't divide by 2, but he didn't. And the only thing I'm like, why didn't he divide by 2? Because the amplitude, because this is corresponding with a cosine, because this is just Euler's identity, it's made of cosine and then theta plus cosine theta over 2. Cosine theta plus cosine negative j theta all over 2. And he just took the amplitude and squared it, but he didn't divide by 2, which I might ask him on, but that was in his notes, so just go with that for now. But for all the other examples we've done, it's always been when it's a coefficient of like a cosine or sine, it's always a squared over 2. So just like a heads up, I'm not for sure why he didn't divide that one by 2. And so now that we got that done with, we're going to go on to the next, which is the Fourier transform, which is basically our last one we're going to encounter here and what we're going to focus on for the remainder. So the Fourier transform, what is it? Why do we use it? And so here, I will give you guys exactly like 2 minutes real quick, and then we'll come back. Okay, so we're going to talk about the Fourier transform. And so the Fourier transform, what is it? It basically represents a continuous time non-periodic signal. And in the frequency domain, so x of t, frequency domain. Okay, so for non-periodic signals, basically what we're going to see is for non-periodic signals, we have x of t is equal to 1 over 2 pi, and then from negative infinity to infinity, and then it's capital X, and then omega e to the j omega t d omega. And this is the Fourier transform of x, expression of x of t. And so the actual Fourier transform is given by here, where it is x omega is equal from negative infinity to infinity, and x to t e to the negative j omega t dt. And so this is the actual Fourier transform to be familiar with. And so this is the Fourier transform right here, this from right here. And so you're going to see this throughout your entire career in EE going from this point forward, so get used to it. So x omega is called the frequency domain representation of x of t. It's common to use capital letters, and basically it's a function of frequency. That's what we're seeing here. And sometimes you'll see x of j omega, sometimes you'll see x of omega. And so it's basically one or the other. And what we're going to see is, let's do one example just to start it out. So x omega is going to be, So find the Fourier transform of, and then it's x of t is equal to e to the negative at u of t. Then a is greater than 0. We told us that. So x omega is going to equal from negative infinity to infinity. And then it's going to be x of t e to the negative j omega t dt. That's literally just pulling it from this equation here. And I highlighted. And then so we're just using that equation to find the Fourier transform. Here's our x of t. So let's just plug in our x of t. E negative at u of t e to the negative j omega t dt. And this is going to be Well, the U of t will cause this lower bound to be 0. The e to the, and then it's going to be minus, and then it's a plus j omega, and then t dt. This is going to be negative 1 over a plus j omega, and then it's going to be e, let's see, this is the antiderivative, e to the negative a plus j omega t, and then it's valued from 0 to infinity. So that's the antiderivative we're doing. And we know, okay, if we plug in infinity here, a is greater than 0. So this would be, well, our frequency is a positive number. So this is a positive number. So it's e to the negative infinity, which is 0. And so this term evaluates to 0. But then when we have 0 plugged in for t, it's going to be negative 1 over a plus j omega e to the 0, which is 1. So it's going to be, so this would be 0 minus, and then it'd be negative 1 over a plus j omega e to the 0, which goes to 1. So it would be just 1 over a plus j omega. There you go. And that would be the Fourier transform. So it's literally just this integral, which is nice. And so just be careful with the e to the negative j omega t. And then what you're going to have is, let's look here. We're going to notice that for non-periodic, continuous time signals, like x to t, the Fourier transform which is capital X omega, is a non-periodic continuous signal in the frequency domain. And so that's omega. So what we're going to notice is that basically x omega has a continuous spectrum. Whereas when we did Fourier series, it had a line spectrum. It was discrete, remember? It only took on certain values. It wasn't continuous. And then so we're going to notice that x omega is a complex function, which means it has phase and magnitude. And so we'll also notice that has a Hermitian property. So it has Hermitian symmetry, which tells you that x to the conjugate of x is equal to the negative value of omega evaluated for x. And so this is just basically saying for our magnitudes are even, but our phases are odd. So basically shows us that the magnitudes are the same, they're even. Oh, sorry, I don't know why I wrote. That's an x there. X and then negative omega, which is equal to x conjugate of omega. And then our phase is going to be phase of x omega equals the I'm looking real quick from our old definitions of Hermitian symmetry. And when we've done Hermitian symmetry before, we've always written it in this format. So I think he's actually wrong. I think it should be this way. That's what it should be, because that's what Hermitian symmetry always is. I think he made an error. And so if x to t is real and even. So this is a big thing to notice is x to t, when it's real and even, that means your phase angle is either 0 or pi, because that's real. Remember, if you have your real axis, it's always the x-axis, so it's real and even, it's either 0 or pi. But if it is odd, then it's pure imaginary, so it's either pi over 2 or negative pi over 2 for your phase angle here. And so let's find the Fourier transform. So we're going to do an example. So this is the Fourier transform of you're going to have x of t is equal to rectangle of t over tau, and then it's equal to 1, 0. So it's 1 for t over tau is less than 1/2, but it is 0 for t over tau. It's greater than 1/2. And so if we have our t over tau, let's just draw a diagram. This is our negative tau over 2, and this is our tau over 2. So it's going to be wait, t over tau. I think, yeah, no, this is t over tau. Sorry, t over tau. This is t over tau. Okay, and so, oh, wait, but we need to do it when it's divided by 2. And so it would be 1/2. Okay, if we're putting this in terms of t, sorry, for axis, this is actually good to take. We would have to multiply this, so it would become tau over 2, right, to get t by itself. So it would become t is less than 1/2 tau, and then t is greater than 1/2 tau. And so this would be, that's why I had tau over 2 originally, sorry. And then negative tau over 2. Okay, there you go. So now we got our rectangle, and we need to find the Fourier transform. And so the Fourier transform, let's just write the integral from negative infinity to infinity. And it's going to be x of t e to the negative j omega t dt, which is going to be, here we have tau over 2 to negative tau over 2. It's non-periodic, so that's why we're using the Fourier transform. And the area only occurs between these two values where it's 1. And then so we just have 1 for x of t, and then it's e to the negative j omega t dt. Well, this is going to be negative 1 over j omega, and then it is e to the negative j omega t from tau over 2, negative tau over 2 to tau over 2. And when you evaluate this, this is going to be negative 1 over j omega e to the negative j omega tau over 2 minus negative 1 over j omega e to the negative j omega negative tau over 2. So this would be plus, so it would be 1 over j omega. So what we're going to see here is we're going to get negative and a plus, but this would be e to the j omega tau over 2, 1 over j omega, and then plus negative 1 over j omega, e to negative j omega tau over 2. And so if we combine, let me see, this, remember, we get e to the j omega tau over 2 minus e to negative j omega tau over 2 all over j omega. And so e to j theta minus e negative j theta all over 2. Okay, remember though, we have this cosine property. You remember from Euler's identity, cosine theta is equal to e to the j theta minus e to negative j theta all over 2. So here's our theta, but we need to tune the denominator. So I'm going to multiply in the front. Let's see. Oh, wait, no, this is actually sine. Sorry, give me a sec. Real quick, Euler's identity. Yes, this is sine. Sorry, because there would be a plus in between for cosine, but for sine of theta, It's equal to e to the j theta minus e to the negative j theta over 2. So we have a negative in the middle, so we need to turn this into sine of theta. So we need, the j tern's good. We just need to get this omega term out. So we're going to do, let's see, how would we get rid of that? We would have like a, we need to multiply, like have a, well, we need a 2 in the denominator. So if we have a 2, and then if we have over j to omega, those would cancel, right? So we e to j omega tau over 2 minus e to the negative j omega tau over 2. So those 2 would cancel. Now I just need to get rid of the omega. And so if I were to get rid of the omega, what do I need? I could just pull that out and just rewrite it such that I would get 2 over omega, and then e to the j omega tau over 2 minus e to the negative j omega tau over 2 all over, and then this is going to be j. And so now I can write it as 2 over omega, and then it will be sine. Then it's going to be of omega tau over 2. And now I have it like that. If you would want to put it in the sinc format, which sinc, remember, sinc is going to be your, sinc of theta will equal your sine of theta all over theta. And so here we have our sine of theta, but we don't have it over theta, which is tau over 2. So, but we have a 2 up here. So if we do 2 over omega, and then what do we need to do in order to get this in the denominator? Omega 2 over 2. So I need to multiply by, let's see, omega 2 over 2. Okay, what if I do a omega tau over 2 all over, and then if I did sine of omega tau over 2. So this omega tau over 2 in the denominator cancels the 1 that I multiplied in the numerator. So secret form of 1. And this would then equal, well, these ones cancel. So these ones cancel. So it'd just be tau sinc of omega tau over 2. That's how you would get that answer. Okay, now we got that. Let's look at the Fourier transform of this one guy, and then let's see, is there anything else I want to focus on? All the way up to example 7. So let me see. Let's do these two, and then we'll call it a night, and we'll be good at that because it's 8:13. So this one says, find x of t if x of omega is equal to 2 pi delta omega. So your x of t, remember, we have to convert back when we're going over Fourier series. X of t is given by this formula here. So I'm going to recopy that formula. 1 over 2 pi, from negative infinity to infinity, x of omega e to the j omega t d omega. Here we have 2 pi omega, sorry, delta omega, e to the j omega t d omega, negative infinity to infinity, 1 over 2 pi. Okay, this is going to be, well, this 2 pi cancel this one, so that would just be 1. That's a constant in front. Then delta omega e to the j omega t d omega. Well, what I can tell you about this is this one is the sampling property. If you remember, so we can plug in what we have here, which is -0 for big T. So this one evaluate at 0 would be 1. And so then it would just be negative infinity to infinity delta omega d omega, which is just equal to 1. Due to that, sorry, I think it's a shifting property, sorry. And so the shifting property, if you remember, if you don't, that's fine. Delta, and then remember it's like t minus tau, and then x of t. That is equal to delta t minus tau, and then x capital T. And then you can just plug that in here. So here it's -0. So then we plugged in 0 for here because that's our x of t. Then the last one we'll do is the Fourier transform basically of this one. So it says x to a t equals e to the j omega naught t. So find Fourier transform of, and then we're given this. Well, remember, our Fourier transform is x to omega is equal to negative infinity to infinity, e to the j omega naught t, e to the negative j omega t dt. Well, this is going to be, we can combine these, so it would be negative infinity to infinity, then e to the t, so then that means j, what did I say? Fourier transform to this. Omega naught is going to be, okay, it still has a j term in common, so let's see. That would be then, so jt are in common to both. So then it'd be omega naught minus omega, and then dt. And then looking at what we have here, well, what should we do? Let this exponential need to see. Let's look at the Fourier transform if it's two. Okay. Let's see. 1, 2, 3, 4. Okay. If we think about this, if we have this specific input, that would just be okay, think about this. What if we had another one? Just going off what I recall, it's equal to 1. And so what if we were like, oh, what is the Fourier transform this? We'd have x3 of t would equal negative infinity to infinity. And then it would be 1 e to the, and then it would be negative j omega naught t dt, which we have discovered when we've done that, it was 2 pi, then delta omega. And then because we know that comes into being, remember, because just from this example up here, we got 1 from 2 pi omega, sorry, 2 pi delta omega. So here, since we know 1 produces this result, then what we're seeing here, what the difference is this x3 is 2 pi omega naught. We have an e to the j omega naught. And so it's just causing here in our input C, we have a delay in here. So this can be written as, well, what if I took out instead, if I did negative infinity to infinity, I did e to the negative j t, and then it's omega minus omega naught dt. Okay, if we format it in this way, we're gonna have it so that this is very similar to what we've done before. But the big thing to notice is that here, instead, we just have a minus omega naught. That's the only difference. So we just have a phase shift. So shouldn't it just be a phase shift in the output since it's a linear time invariant system? This one matches this one, correct? Exactly the same. So this should just be 2 pi delta omega minus omega naught. That's how this comes into being. Is because if we look here at our original table, this e to the negative j omega is here, but the only thing here is we have a phase shift. So we just take that phase shift into account in the output. That's how we get our answer. And I will stop the recording